Hello, ladies and gentlemen. Good to see you again. This is week 2, lecture 2, and today we're going to be focusing on an introduction to geographical data, some of the issues around geographical data. It's important for me to just say that this week we're going to have the first homework, so you need to make sure that you've got the software installed on your computer and that you've followed the previous lectures and also the previous lab, because the homework for this week is going to be building off that previous content. Remember that it needs to be submitted before the following week's lecture on the Thursday. I won't accept any late submissions, so make sure you do get it in on time. I held a Q&A earlier this week and we only had a few people there. I am giving you my time during these to make sure that you get the most out of the course. I really want to help you. If you're keen to engage, I'll give you my time, make sure that you develop and really get the best out of what is a really important skill set. I'm going to be holding another one today. I don't want people to come and ask me and say that they can't install our studio next week, essentially. I mean, you've had plenty of opportunities now to look at the material and to have a go. So this really needs to be done and dusted this week so that we can move on with actual content and not get left behind in the future weeks of the class. So let's get on this. Let's have some motivation and let's get the most out of these couple of weeks where the workload is lighter than it will be later in the course, because things are going to get progressively harder, and also build on the content that we're covering now. So what's the point of the lecture today? Well, essentially I want to introduce you to these different types of data. A lot of this will be similar to maybe some of the data types which you've been taught in other statistics classes. So I noticed that some of you have done previous classes which are like this one here, like GGS300. But we will be focusing also on spatial issues relating to this data. And that's really important because these are things which you need to be cognizant about when you're actually focusing on research questions in the spatial sciences. So we all see quantitative information on a daily basis. We're always engaging with it. Well, what are those sources of data and how are they represented? So I'm going to keep coming back to the smartphone example. So we have apps on here and we're being tracked pretty much continuously. So all of our GPS coordinates also can be taken off here. So I've given you an example just here of some of the information which I get on a daily basis. So this is off my Fitbit. And this is a relatively simple dashboard here. We can see on the left, it's just giving me an estimate of the number of steps that I've taken today. So that's basically from the movement sensor within my smartwatch. And then the actual distance here, essentially that can be calculated fairly easily from the lat long coordinates, which my device is collecting as I move around spatially. And obviously all of this is generally being aggregated here, so it's not giving as much spatial information at all. It's very simple. On the right hand side, we've got temporal data. So this is my resting heart rate. And essentially this is the resting heart rate over time for the last 30 days. So it's taking an average of my resting heart rate on a daily basis. And then this is just plotting, saying where I probably have or haven't done enough exercise. But this is the type of information which many of us are engaging with on a regular basis as we move around an environment. So it's spatio-temporal. It's also picking up the temporal dimension too. What other data do we engage with regularly? Well, this is market data. So this is just a snapshot for yesterday for the S&P 500. So the 500 largest companies listed on US stock exchanges. Obviously, the markets are very hot right now. So you can see the dip here from COVID. And actually, the stock market's picked up very quickly to basically, they've gone above where they were back in February, March time. Which is, in many ways good, but it's looking like things are pretty overvalued right now, and there's an issue there if at some point it drops quite considerably. But many of us are engaging with this type of market information regularly. You know, if you if you go to a website like this, Market Watch, then you're able to dig into this data, whether you want to focus on different temporal periods or different exchanges, which obviously are located in different geographic regions. So whether that's the New York Stock Exchange or Chicago. But here, generally, it's all being aggregated, and it's less relevant to this type of data. Census data. So I use demographic information all the time in pretty much all of my models. So if you haven't visited the Census Bureau yet, then I'm sure you will do by the time you finish your time here at GMU for whatever project you're working on. I mean, having an understanding of how many people there are in different location is really important. But then also the demographic characteristics of those people. So what are their ages, what are their gender, things like this are really important because it might affect how we use technology, for example. You know, if you've got teenagers, then their technology usage and adoption rate is going to be vastly different to elderly people, for example. You think of the level of video usage, say if you looked at 13-year-olds up to 25-year-olds, and you looked at the amount of data that they were generating on smartphones and compared it to people who are over 60, then basically all of those uses of video on here, whatever that is, so that's Instagram, TikTok, Facebook, whatever, YouTube, then that's going to be generating far larger amounts of data. So it's really important to have an understanding of the age of different people, and obviously that is located in space, and that's a fundamental part of spatial analysis. You know, if we're building integrated assessment models, whether it's to assess climate change or to look at energy access or to just roll out broadband to people who don't have good internet, then you need this type of information essentially to help build models which improve decisions. Weather data, we engage with weather information all the time, and this is highly geographic in its content. Granted, it's often reduced down to a fairly simplistic form. So just as an example, here's a hurricane path, and it's been forecast. So it's going up from Cuba through the Gulf of Mexico, making landfall around the western part of Florida, predicted to go up through Georgia, South Carolina, and then carry on up the eastern seaboard. Ultimately, this could be actual information where we're tracking a hurricane moving, so over space, over time, or it could be a probabilistic assessment of where we think it's going to go. So this could just be a model-based estimate of which path we think it's going to take, and obviously that forecasting is really important. But this just gives you an example of how we kind of take very complicated, very complex models, which often produce vast quantities of data, and then we're able to reduce it down to something that we're able to engage with on a very easy, on a daily basis in a very easy way. So this isn't complicated to understand. Most people can understand a map. They understand maybe where they are on the map. So this type of information we're engaging with regularly. So they are some of the types of information that we have. Then the question is, well, what are the types of issues that maybe you and I need to consider when we're doing research in the spatial sciences? So we covered in the previous lecture that quantitative information is essential for science. So we're able to, as a consequence of standardizing the collection of this quantitative information, then essentially start to ask questions relating to why processes happen, why they happen where they do, and how do these processes happen. And generally going through that thought process, understanding things about the past, for example, how processes have played around, how processes have played out in the past, consequently can help us to understand how our decisions may affect the future, which is obviously hugely important and one of the main reasons for why we do what we do here, to help try and make better decisions for the future, and hopefully that will make people's lives better. So I'm just giving you an example here, and my question is, how do we provide universal broadband access to countries across the African continent? And I'm giving you this because I'm working on this problem at the moment. It's highly spatial, has a lot of spatial information, and we've got some nice pretty plots here. So you can see on the left-hand side the population density. So we can see these huge clusters of population along the North African coast, from Morocco along to Tunisia, through Algeria. And then we have this huge expanse of very few people, which is basically the Sahara area. And then all of the population, a lot of the population is clustered along the west coast of Africa here. We have lots of areas with low population around here. And then we have the East African area, so around Ethiopia, and then around Lake Victoria, so Uganda, Rwanda, Kenya, Tanzania. And we can see that the population obviously is highly spatially heterogeneous, so that means it's very different. When we look across space, the population is clustered in space, essentially. These types of agglomeration effects for how people cluster in space leads to all sorts of challenges for how we deliver, for example, basic infrastructure services. So whether you want to access energy, or whether you want to connect to the internet, or whether you're a government and you want to build new transport links because that's important for economic development. This issue about how you do that in a cost-effective way is challenging, and that's often where spatial science can be involved, building models. So the question here is, how do we do that? I've given you an example on the right of what the costs could be for delivering that universal broadband access, and you can see that it's much higher in areas where you've got lower population density, and this is one of the challenges. So this is just a general problem which includes spatial data, which I've been tackling with, that I want us to talk through. So the question is, well, what's the research question? How do we start thinking about this? So we know that maybe we have this aspiration of delivering internet to people who aren't currently connected. Maybe only about 40 to 50% of households in countries across Africa have access to the internet. But we know that accessing the internet is revolutionary in terms of the economic and the social benefits that it can provide to you and I. And we want that people, therefore, to have access to this tool. So really, well, how do we do that? These infrastructures and these technologies are going to be delivered through markets, which means that people need to be able to pay for them. They need to be viable. Economics governs pretty much all of our daily interactions. And therefore, well, the question may well be, what's the cheapest way for us to actually deliver this infrastructure, given the fact that maybe people in these areas, these parts of these countries are generally, they might have low incomes because these are low income countries. And therefore, we need to be able to make sure that we can deliver these services in a cost efficient way. So that's a good start. Then the question may well be, well, what type of data do we need to actually tackle this problem? And I've already spoken at length in this lecture about the importance of demographic information, census information, and that's a prime data input for this particular issue here. So where are people that are currently not connected to the internet? So you need two types of information there. You need a population data layer, which we can get thanks to a lot of the global population satellite sense data sets, which are now becoming very prevalent. So that's the first piece. And then the second piece may be where the existing cell phone coverage is. So maybe we have a spatial layer which says that in these areas you're able to get a 2G voice signal, and in these areas you're able to get a 4G data signal, so you can access the internet pretty well. And then what we want to be able to do is take the population data layer and then also the infrastructure layer for internet access and intersect them. And then when we intersect them, we're able to have a better understanding of which places are well connected already, and people can therefore get access to the internet. Maybe they aren't accessing it due to other issues. And then maybe those other areas where there isn't any current infrastructure to access, and therefore there's a digital divide, and therefore maybe we want government to help subsidize the build out of infrastructure to those rural and remote areas. So that's an example of the types of data that we might need. We could also have spatial boundary data there. So maybe the population data layer, for example, is at a 1 kilometre square granularity, so it's very, very granular. Maybe what we also want is statistical boundaries so that we can aggregate that data up to the political boundaries, so that we have a better understanding of what the conditions may be in different areas based on the people who may actually make decisions about how resources are spent. So that's just a little bit of an example of the types of data that we may need to investigate this particular problem. How do we collect the required data? Well, this is definitely a hard problem if, for example, you're in the social sciences and you have to go out and you want to collect survey data. You want to go and survey people. Surveys in general are very expensive. They're expensive in monetary terms, and that's partly because they're expensive in time. So if you need to go and you need to individually speak to X number of people, or you need to individually send out a form to X number of people or a survey link, that could be quite expensive in terms of how you do that, and therefore that means it's expensive overall. For the problems that I'm working on, I try to avoid using any survey data because of that issue. Thankfully, you're in a geoinformatics department. A lot of the geoinformation these days that we are able to obtain from satellite imagery is fantastic, and that means that we're able to overcome some of these issues of trying to collect data at a very local level. So just to give you one example, I have a new paper, which is a working paper at the moment, which I've been producing with a colleague at the Center for Supercomputing Applications at the University of Illinois Urbana-Champaign. And that paper takes satellite imagery, and we basically use a machine learning model which estimates what the socioeconomic conditions are on the ground simply by showing the model a satellite picture, essentially. And we're able to train that model by using actual survey data that we have for about 800 different locations, for example, in Malawi or Ethiopia. And then we're able to take the satellite images for those locations and say, well, these are the conditions that we know are on the ground, and the model's able to learn, well, maybe places with better socioeconomic characteristics have square buildings rather than round buildings, and maybe they have a corrugated iron roof rather than an organic material roof. And essentially then when we train this model, we're then able to just show it a picture of a satellite image, and it's able to make an educated guess as to what the socioeconomic conditions are on the ground. So maybe how much income the people living there have, and that's an indicator of poverty. So that's a really positive step that's starting to come through in the literature now. And that approach is about 20% more effective than merely using more basic methods of data estimation, such as the amount of light emitted at night. So luminosity from lighting, because before people were essentially making the link between the fact that if you had electricity access, you were therefore you had a higher income. So people were able to scale the luminosity emitted at night into the sky using satellite imagery and make an estimate of the on-the-ground conditions. Well, this satellite imagery approach is twice as effective as that particular approach which I mentioned. So anyway, the point is, these days we're going through a data revolution, and it's a lot easier for us to remotely sense some of the required data that we need and make estimates that way than it is to go out on foot and essentially try to collect vast quantities of data, which essentially is expensive. So that's a little bit of thinking about what the research question is, maybe what data we need, how we collect that data. The question then is, well, how do we actually use that information in the scientific process? And I spoke previously about the scientific process in the first lecture. For those of you who have done the required reading for the course textbook, here you'll recognize that this process is built off what's reported in the textbook. But it just gives you a general framework for how maybe we carry out scientific research. So we can start with a problem that we have. Maybe we want to connect more people to the internet. We then need to think about how we develop questions to investigate this problem. So, well, why are people not connected to the internet? What's the most effective way to connect people? What's the cheapest way? What decisions can help build more infrastructure in places maybe where we need more economic development? And then essentially we're able to prepare any data that we need, process that, and generally reach conclusions from the kind of descriptive data that we might have. So that might be mapping the data, looking spatially at the processes. So I showed you before the picture or the image of population density across the African continent. That's a good example of how we can spatially map these processes and then kind of qualitatively understand what's happening geographically by looking at that data. And then we may go one step further than this. So this is really the preliminary part of this process, and maybe it's quite close to what we're going to be doing in the first couple of weeks of this course as we move on to descriptive statistics over the next 2-3 weeks. Then we might say, okay, well, I've got a reasonable idea now of the processes that I think are happening here. I'm going to make some statements about how I think the world's going to work. So I'm going to formulate hypotheses. And then once I've got those hypotheses, I'm then able to use inferential statistics, essentially. So we're able to take data and then test whether I think the hypotheses that I've made are supported by the underlying data that I've collected and built a model for. It's very hard to often have conclusive evidence. It's very hard to have truth. That's why there's such a strong emphasis on theory. Obviously, theories haven't been proven yet. They're just suggestions of how the world works. But this process allows us to develop indicative evidence, which is very important. And this helps to make the world a better place by actually feeding that evidence through to decision makers. And those decision makers may be in government, they may be in industry. But by having new information about how to invest limited resources, for example, then we can actually gain real-world impact from the types of academic research that we're doing here, maybe using spatial statistics or spatial modeling processes. So that's a general framework for how we might use some of this information. There are, of course, a variety of different issues that we all need to be aware of when we're using this data. And here we're going to go over 4 different types of issues that are going to be present within spatial geographical data sets that we all need to be aware of. And, if you go on to do research, or you go on to even just do a dissertation as part of your degree here, then you're going to have to think critically about the methods that you use in that process. You're going to have to reflect on the advantages and the disadvantages of those different methods. And that's why we need to consider these types of issues that I outline here, which we're now going to drill down into in depth. So, boundaries. Boundaries are one of the things that genuinely keeps me up at night, and I know that's sad. But when you actually look over model code, or you look over your results and you start trying to use these types of models to actually answer real world questions, often 2 of the main things that can cause uncertainty in your models are, number 1, unit errors. That happens regularly. This is really important. That's why you need to test your code. So have you got the right unit in the first place? Is it definitely kilograms? Is it definitely square kilometers, not meters squared? You have to be aware of what the unit is, but also you need to be cognizant of the way that you design the model. And here I'm talking specifically about the zoning boundary issues. So if you use different sized boundaries, or you place the boundaries in different places, then you may well get a different answer. And that is concerning because you want your model to produce ideally accurate and ideally also precise results. And any issues, such as the ones I've just highlighted here, can either give you completely wrong results, such as with unit errors, or they can introduce uncertainty into those estimates, which affect your ultimate results. So why does this happen? Well, boundaries ultimately are artificially imposed. Often they're political boundaries, and they're created by us, by governments, for example. So just to give you approximate case, here we've got the census boundaries for Fairfax County. And they are not boundaries that have occurred naturally. Granted, it does follow some geographical features, some of the boundaries here, but generally if you look at the census tracts boundaries, they are artificially imposed, and that means that they're going to have some influence over your results as you start to aggregate or work with data which fall within these boundary patterns. So then I guess the question is, well, what happens if you use a different type of aggregation pattern? So here we're using 1 kilometre squared. This is just an example which was easy to extract for Germany on the population density. And you can see here that it's much higher in Dusseldorf, for example, as opposed to some of the rural hinterland around. But as you're going to 1 kilometre squared, it's obviously a very different geography from some of the boundaries that we looked at for the US census tracts. Generally in my work right now, I'm using a mixture of the 1 kilometre squared data set and then the political boundaries on top, because it allows you to capture the nuance of the detail at the local level, and then you can aggregate it to the level that you want in order to report the results. You can also understand some of the sensitivities of these issues that we're talking about here. So why is this boundary effect an issue? Well, actually, it's got a formal name in the literature, and that's the modifiable areal unit problem. So essentially, this is a problem which comes in 2 different formats. One is the scale effect. So I mentioned aggregation just there. What level do you aggregate the data? So how large are those boundaries that you're going to pick? So that's the first issue. And then the second issue is the zoning effect. So where do you actually draw the boundaries? Because that's also going to affect the result that you get at the end. And here's some very simple numerical diagrams just explaining how you can have similar data but you get different results based on how the patterns are drawn. So this is an issue which we all need to take seriously and be aware of. So the zoning issue. Why does that happen? So I'm just going to give you a very simple example here. So maybe these are points that we want to sample. Let's just assume, for the sake of this being simple, that these are just points in space, and we want to understand how many points there are in each area. If I use this particular boundary set 1, then essentially we have 6 points that we want to sample here, 2 points here, 0 in this box, and 11 down here. So if we actually look at the total number of points across my sampling frame here, of 4 different tiles, we get a mean of 4.75 points per tile, okay? But only a small change in the boundary positions, as I've emphasized here, for boundary set 2, provide quite different results. So here actually now we have 8 points within this first tile, 0 points within the second tile, 0 points also in the third tile, and then 13 points within the fourth tile. So then actually when we take the arithmetic mean, here we're getting 5.25 for these same 4 tiles, just because of the very minor change in the positioning of these boundaries. So that's a simple example of this issue. Actually, this zoning issue also of where you then draw the boundaries has a very real impact on our lives. So, for example, I just gave you quite theoretical cases of demonstrating in the simplest possible way how this can occur. But actually, here, when we talk about political boundaries being gerrymandered, essentially, so this is the name for changing the shape of the political boundaries in favour of most usually the party who's actually in power. So just to give you an example of this, we have a set of precincts here. 60% are yellow and 40% are green. And actually, if we just draw the boundaries here, so that the boundaries are basically horizontal, then yellow wins at every opportunity. But if we look on the right-hand side here, where the boundaries have basically been gerrymandered, although it's the same voting preferences overall, actually the green wins the majority here. So this is really important. And there's a second example just down here. But essentially, this is a very real problem. Some people use it to take advantage of the system, essentially. So that's the zoning issue. What about the aggregation problem? Well, scale is important. So I mentioned before about using 1 kilometre squared areas versus maybe statistical boundaries for political areas which maybe are much larger. And actually, you get an averaging effect when you start to use different boundary sizes. So often, if you're using higher aggregation boundaries, then you might be averaging away a lot of the spatial heterogeneity, so the spatial differences that are present at a local area. So, for example, you might have in a large area, take a state, for example. You take New York State, you're going to have really quite rural areas if you go upstate to the northwest area. But then you also have one of the most agglomerated cities with some of the highest population densities anywhere in the world, if you're looking at Manhattan, for example, in New York City. So these are issues which you need to be aware of when you're choosing a scale of aggregation, whether that's local or whether that's at a high level. But generally, you need to be aware of this to reflect the process in which you are, the process which you're studying. So if you're studying a process which does take place at the very local level, maybe housing markets are a good one because from block to block, there can be quite different price differentials. Maybe you do need to be quite spatially differentiated at that level. Whereas maybe other processes can be looked at a higher level. And you, as the research scientist, need to make that call, and you need to justify it in your work as to why you've chosen that particular aggregation level. There is also a reason for choosing a certain aggregation level, and that's just the computational ease with which you're able to aggregate the data and run the model that you've produced, for example. So too many times I've chosen to use quite spatially disaggregated data, and sometimes the model is just too large to run on a single machine, or just takes too long, or it's just far too cumbersome. You don't want to be running a model for days and days and days on end. It's a real issue. By the time you run it for 3 days, you find the results wrong, and then you have to rerun it again. So it's a good reason for starting small, but also with small samples of data, but also choosing the right aggregation layer. So if you can do something at a layer where you only have a reasonable number of statistical units, so maybe not census blocks, maybe you're using city boundaries and intermediate geography, then that might be much more sensible for the problem that you're working on. Unfortunately, there are no hard and fast rules. You just have to experiment and play with the data. And you generally need to pick something that, at least for geographical work, that has some decent spatial resolution if the data is available. So consider aggregation. So you end up with small or large averaging depending on that level of aggregation which you're using. So logical fallacies. Well, what's a fallacy before we get to logical fallacies? Well, the Oxford English Dictionary definition basically states that a fallacy is a mistaken belief. Or more importantly to what we're doing here, it's mistaken reasoning to the extent that it leads to an invalid argument. And this is absolutely essential for what we do, because the logic for how you build a model, produce results, and use that evidence to influence government, for example, to make better policy decisions, comes under a lot of fire when you get to that level of evidence influence. And therefore, you not only need a thick skin, but you need a solid logic for why you've made decisions about the process which you've statistically modeled, for example. So a logical fallacy is essentially where inferences on the attributes of individuals, for example, come from group inferences. And this is just one example of a fallacy. There are a long list of different types of fallacies that exist. But here is just one example to give you a bit of a flavour. And just to take that previous example again, so if you said that New York State has a high population density, which is in reality being driven mainly by New York City, you could say that you could say, sorry, that New York State has a high population density, when in reality it doesn't. It's a lot more spatially nuanced than that. So an individual from New York City has a high population density. Is from a dense city. But this is one of the issues with making those aggregation decisions, which I mentioned before. And actually, I was just working on this yesterday, and we were using population density to make judgments about costs. And it's exactly this problem that metrics like population density, particularly if you're taking them at the state level, may not be that relevant at the local level, because there are other spatial processes going on. You know, it really depends on how the population is agglomerated within that quite large area that you're using to draw as the boundary for which you then produce your population density metric. So this is really important. You need to keep it in mind for both aspatial and for spatial statistics. So there we've covered 4 different aspects of spatial data that will be important when you think about the scientific research process in the spatial sciences. Now we're going to focus on the types of different data. So we mentioned in the previous lecture that we have both quantitative data, which is essentially numerical, and then also qualitative data that is non-numerical. So essentially it could be text, for example. So I think we've covered this before, so I'm not going to spend too much time on it. We do have this difference between spatial data and non-spatial data, or as I previously referred to it as aspatial data. So spatial data generally has quite explicit geographical characteristics, and often that can be in terms of coordinates. But it could be implicitly spatial in the sense that maybe if you have an address, that might be text, but then you're still able to extract some geographical information from it. And I do that quite regularly. You don't always have data that has geographical information. Often you might have to merge it with other data sets in order to gain some sort of geospatial insight about it, particularly given logic, for example. So if I know that X and Y are related and I've got data on X, and I've got geographical information on Y, but I don't have it for X, then I'm able to relate them together and make some sort of estimate about the geospatial location of some of these entities that I'm interested in. And that can be useful for modeling because you don't always have the data which you really want. So that's spatial types of data, and then non-spatial data will just be data that has essentially no geographical information. Temporal versus atemporal. Everything exists in time. It just depends whether you're actually recording that temporal information with the data which you've produced. So we've touched quite a bit on temporal data already. I used it in some of the earlier examples of the technology types, and obviously the faculty in GGS has a lot of expertise in spatiotemporal modeling, so modeling processes which take place both across space and across time simultaneously. The hurricane modeling that I spoke about earlier with the weather data is a good example of this. So the level of aggregation within your data is important. So maybe an individual exists in space, but then maybe you've also spatially aggregated that data. This is very common, and I mentioned about the Census Bureau data. And there we have data which we've probably collected from an individual via survey, or we've estimated. And that just represents an entity, maybe an individual person or a species type. And then actually when we have spatially aggregated data, what we're essentially then saying is that within some sort of boundary, we might estimate or define the number of individuals living within that boundary. And then we can produce different statistics within those boundaries which we've spoken about. The issue, therefore, of course, is that you're averaging away a lot of the underlying detail and information, and it's quite hard to then kind of reverse engineer the underlying data, so to spatially disaggregate that data again. It's hard to do that robustly, so I do it quite regularly, but you need to have a logic behind why you're doing it, and you need to have some way to validate that the estimates that you produce are sensible. If you remember, we focused on data frames in the lab last week, so types of data, and in the data frames that we focused on, we actually had individual observations which spread as an individual row across the data frame. And actually, if you remember the example that I gave, it was of a person. We had a list of people going down in each row, and that individual in the row had an eye colour, a height, a hair colour, and that's a good way to think of how you may have an individual. So discrete versus continuous types of data. So discrete data essentially is finite, so there's some restrictions on the values. So the number of people in a city, for example, or the number of people in an area, you can't have 2.5 of the person, and you can only have a whole number of an individual. So it's actually discrete in how it's being counted. And that's sitting in terms of, it's juxtaposing continuous variables, essentially, which have an infinite number of possible values and decimals. So if you think of how we define distance, in reality, we might define something as a kilometre or a metre or a millimetre, but actually we can keep going down and down and down and down until we find infinitely smaller portions of that individual unit, and that's why it's continuous. We normally impose some sort of decision on how we report that type of data, so that the units roughly match the process that we're actually focusing on in the analysis. So what about data measures? Well, we've got 4 different types of data measures that I want to just quickly cover here, and I know some of you have covered these previously in other statistics modules, so if you haven't come across these measurements before, then pay attention and make sure you learn them now, and if you have, then hopefully this will just be a quick brush up on your existing level of knowledge. So nominal data, think of this as categories, think of it as quite qualitative or descriptive, think of how you're able to classify, and essentially good examples of nominal data may be the sports team that you support, for example. It's qualitative, you're able to put someone in a particular category, and it's often mutually exclusive. And it contrasts with ordinal data. So maybe nominal data, you don't have any specific relationships in terms of ordering across the different categories that you have. But if you actually focus on ordinal data, imagine that these are categories that you then are able to rank. So imagine you put people into colleges. That on its own could be nominal, but then if you actually had a ranking for those colleges based on some exogenously defined assessment criteria, then actually that would be ordinal data. So the key here to remember is that ordinal sounds like order, and therefore you can think of it in that way. And you can have either strongly ordered data or weakly ordered data. So if you're looking on TripAdvisor and there's a ranking between 1 and 5, then maybe that type of data is relatively weakly ordered in comparison to a discrete ranking of colleges, where generally most colleges will be somewhere in that ranking based on a discrete number. You can't have, there'll maybe only be a couple of cases where you have colleges which are at the same level, and then you wouldn't say that they're 1.5 in the ranking. You would probably just say that they were equal place. So you can have that type of ordering. Then we have interval data. So this is data where the magnitude of difference can be determined, but maybe the 0 point is arbitrarily assigned. So if you think about temperature, where we define 0 degrees in temperature is arbitrarily defined, and it means that therefore there's some influence over then how we're actually able to manipulate that data. So we can add and subtract, fortunately. Whereas with ratio data, so this is data where we have a magnitude of some particular ratio, and we have some sort of natural 0 point, which is not just arbitrarily defined. We can, as a consequence, actually multiply and divide this type of information. So just one example here, 400 millimeters of precipitation is 4 times as much as 100 millimeters. So we have some ratio between the values that we have. And a good example here is distance or area or family income. So you can just take a minute to look at the type of data that we have here. So on the left-hand side, we have, this is college ranking data for the state of Michigan. Here on the left-hand side, we have the school here. We then have a ranking. We then have an in-state cost, an out-of-state cost for tuition, the number of undergrads enrolled, and the year that it's founded. So I just want you to pause the video, take a couple of minutes to think about what the different types of data are, and then when you've done that, we'll be able to have a think through what the different categories may represent. Okay, great. I hope you managed to pause and have a think at what those different categories were. So let's just have a discussion now. So on the left-hand side here, where we have the different school, this is a category. So it's nominal data. Then we have a ranking here. So again, it's a category, but there's some sort of ordered preference based on some assessment criteria. So this is ordinal, essentially. And then we have the tuition cost, which is continuous. So essentially, we could define that value to whatever level of precision we actually want, and it's based on a ratio scale. And then when we look across here at the year founded, obviously this is arbitrarily defined the year that the college was founded, and therefore it lends itself most suitably to interval type of data. So I'm just going to finish on some measurement concepts. For those of you who have done the reading in the book, you may already have seen some of this. If not, then you need to get the reading done this week. Chapter 2 is what we're going to be reading this week. But essentially, we need to make decisions over the level of precision that we have in our data. So precision is essentially how exact a measurement may be. And it reflects the quality of an instrument, or in this case, the quality of a model or a tool maybe that we've built ourselves. So you can see here that maybe we build an arrow throwing device, it's not actually very accurate. It's not actually managed to hit the bullseye in the target, but it is consistently propelling those arrows into the same part of the target board. So it's relatively precise. There's not too much differentiation over how the arrows are hitting the board. And then this contrasts with this idea, or is separate from this idea of accuracy, essentially, and that's where you have a relative degree of correspondence between a value obtained from a model or an instrument and the truth. This is tricky. If we are building models and we want the model to represent a human process, building the model to actually produce numbers that are reasonably accurate is challenging, very challenging. And actually, I remember when I started on my academic career and was looking at the performance of many of the models that already existed in the literature, they were explaining, between 20 to 30% of the data variance in the data. And that's not very accurate. But that's, for stock markets, that might be the status quo in terms of accuracy. But here, just again, when we look at the arrow throwing device on the target board, we can see that actually some of the arrows are being thrown at the bullseye, but it's not necessarily precise, it's not consistent, and that's because there's uncertainty over where that arrow is going to go each time, and that's why there's more of a spread across the actual target points. So then when we put these two concepts together, we can essentially have a tool or a model which might not be accurate and might not be precise. That's a lot of models. Then we might have an accurate model, but it's not necessarily very precise. I'm perfectly very happy with models that can be accurate and not. Well, I think that it depends on the level of uncertainty in your model, but I'll give you an example later of where I've had to make these decisions for myself. And then this is an example of something that's not necessarily accurate, but is precise. You don't want to go here. You don't want to be presenting models which aren't accurate to 10 decimal places, for example. This is not a good way to display your results. And then finally, this is really the gold standard for where we all wish we were, and that's an accurate and precise statistical model. So what's an actual quantitative example of this? Well, if we had a true distance of 41.71 inches, measurements that were coming out and varying consistently quite far away from the target may be quite precise but with low accuracy. Whereas over here, we might have quite high precision and quite high accuracy. This is quite close to the original number, the truth number, and there's only a very small amount of variance around it. Contrasting with here where we have quite low precision, reasonably high accuracy. Maybe if you were to average these points out, you might get to a value which is close to the truth distance. And indeed, that's often how we approach these issues. We create many iterations of a model run and take the average. It's actually called Monte Carlo simulation. I'm not going to be getting to it here, but I just want you to know that there are these types of methods, and they do help you create estimates when there's a lot of uncertainty within your model, and gives you a good understanding of it helps to quantify the uncertainty within your model. So I've been working on 5G assessments for the World Bank, and I assessed 8 low and middle income countries here which were selected for 5G assessment. So that included they included Malawi, Uganda, Senegal, Kenya, so all in the African continent, Pakistan, Albania in the Western Mediterranean, Peru in Latin America, on the western side of South America, and Mexico. And I had to make a decision, therefore, about how I presented the results. Now, this is a forecast model that represents investment over 10 years. So this is, anything forecasting over a long time period is highly inaccurate. And that's because there's so much uncertainty over the future. But that's not to say that it's not worth doing, it's just that we need to be aware of the issues in the data, and often it's not necessarily the answer it gives you, but the relative magnitude between the different scenarios and strategies that you might test. This is called scenario analysis. So anyway, these are the results for the model which I built for Peru, looking at how many people can be covered based on a commercially viable rollout. So say we have 3 mobile operators who are interested in how much revenue they can bring in and then how much money that leaves for them to invest in 5G infrastructure. And then we want to know how many people can be covered under different scenarios, so how much bandwidth, how much capacity you give to each individual, and under the technology which you decide to use. So here we're comparing 4G and 5G, for example, just to keep it simple. And actually these values represent the population decile that can be covered under a commercial rollout, so essentially viably covered without needing state subsidy. And rather than provide what could be quite precise results, I've actually just said, I've reported just deciles. So I've split the population between 0 and 100% coverage into 10 buckets that go from 0, 10, 20, 30, 40, all the way up to 100. And the point here is that the model is not really accurate enough for me to give precision that allows me to specify that extra digit precision. So I've just used these 10 different variants. So I report down here at the bottom that the uncertainty inherent within the modeling process, so think about the accuracy, is high. So here I've opted to report the results by decile rather than as percentage coverage. So if I used a percentage coverage, there could be 99 degrees of freedom. So that's quite precise, or it's quite a large number of degrees of freedom. Whereas the decision that I chose was only 9 degrees of freedom. So it's quite low precision. Now, what do degrees of freedom mean? Well, essentially, you should think of this as if you have 3 buckets that you can put balls into. The number of degrees of freedom is 1 less than the total number, essentially. And that's because if I put one ball in each bucket, I put 1 in the first bucket, I could have chosen 3 buckets to put it in there. I put 1 in the second bucket, I could have chosen 2 buckets there. Then the final ball always has to go into the third bucket. Okay, and this is important to think about because it emphasizes how many different values the final output could actually have adopted, essentially. And it does actually relate to the level of precision upon which you're reporting your results. It also has a statistical meaning within some of the models that we're going to be fitting later in this class. Okay, validity. Building a model is all well and good, but unless you actually are able to say that the results that are being produced are valid in some way, so that you've been able to validate them, so that means that they're broadly correct. You need to evaluate how well the model results that are being produced reflect some sort of case where you have some actual numbers. This is essential. This is long and hard, and it's hard to do. You have to design your model in a way that allows you to then try to validate the model results that you produce. But this has a specific meaning, the word validity, how valid, how truthful are the results that have been produced. So this is an important concept for you to grasp. And then also reliability is important here. So what's the stability of the results? If you start to change some of the data inputs for your model, do the results change in a way that is similar to how you change those input variables, or as in many cases, does the model do something completely crazy that's not consistent with reality or not consistent with the theory upon which you've built that model? This happens all the time. People build models, particularly complex, big models where you've got lots of dynamics going on, but maybe they're trying to model big processes, and you get these highly unreliable results. And I am not a fan of complicated models at all. I like really simple models that have a few parameters that's able to explain a large amount of variance. And that's because you're able to produce more reliable and consistent results as a consequence. They might not reflect every single situation, but that's a much stronger situation to be in, to have a general model that explains quite a large amount of variance, rather than trying to explain every single nuance about a process, but then producing something so big and unwieldy that you're unable to kind of describe what's happening, or to validate the results, or to easily test your model. And I've just emphasized here that there are particular techniques that you can produce, techniques that you can carry out in order to ensure reliability in the way that you take data measurements, or the way that you produce measurements, you model data. And forecasting is one that is particularly challenging in order to do reliably. Because if you're focusing over very long-term periods, there's just so much uncertainty, so many degrees of freedom for where the forecast could go. Okay, so this is the end of the second lecture. I'm about to do a Q&A with you shortly, so hopefully you'll take advantage of that and will be able to get any problems which you still have fixed. Obviously, now you need to be able to do the homework, which I'm going to set you this week and hand in before next Thursday's lecture. So you've got the lab assignment from last week. I will set the homework up later today so that you've got it. Let me know if you have any issues, but first try to Stack Exchange or Google any issues which you have, and if you do find any, then please do share them with the group. Okay, great. Well, it's good to see you again, and I look forward to seeing you again soon. Goodbye.